Any volunteer? I can tell you, yeah, yes. Oh gosh, hold on, let me get rid of that. Okay, well, I can tell you why I'm here. It is because, and if I can just get rid of this, hold on a second. Unsupervised pattern discovery is cool. Okay, so I'll give you an example. Anybody here seen this movie called The Wild Robot? Okay, in this movie, this robot goes to this island and it can't like communicate with any of the animals or the beings on this planet. So it sits there and just for about a year or two, just listens. And then eventually, after a couple of years, it is able to speak deer, it's able to speak chipmunk. It is performed unsupervised, that is automatic pattern discovery. So that is super cool, right? And that I think is really what we're trying to do as scientists, right? We're trying to, at least pattern discovery, or we're trying to find structure from what could be noise, right? We're trying to model the world and be able to understand it in a structured way. And that is really, I think, what a lot of us are doing fundamentally as scientists. We want to understand so that we can do things like predict and, these sorts of things. So if we can discover these patterns, it's kind of like one building block towards building these models of the world. And if we can do it in a way that is unsupervised or automatic, which we'll talk about today, that's even cooler, in my humble opinion. So just a little bit about where I'm coming from with this. So at the ROSIE lab, as Dr. Faber talked about a little bit briefly, and this is a little bit facetious here in front of like people who actually work with real human brains, but what we think of as the analogy in our lab is that we try to build robot brains, okay, not obviously not biological, software control systems for robots, and in a way that is biologically inspired, if we can, or psychologically inspired. And we specifically focus on this type of interaction here, which would be like a robot that would interact with a dynamic world filled with humans. And so I love dynamics. I'm super interested. I've been interested in dynamics for more than a decade. And what does that mean? It means that if we have humans that are, going around in the world, time passes, so there's going to be some dynamics going on. There's people, and I specifically work on the dynamics in things like the face, so the way our faces move over time, the way our voices change inflection and loudness and so forth over time, how our body gestures over time, and the dynamics of how we move over time. Actually, with the big large language models, for me, it wasn't so as interesting to begin with because I'm not interested in semantics. I'm actually interested in just like dynamics. And I think it could be related to some of the things that some people are doing with brains because we think about how brains also dynamically adapt over time. Some work we also do is how do these dynamics change or adapt to the context that they're in? How do these dynamics work when in concert with other things that are changing in time? So that's called multimodal interactions. So we look at how humans do this and then how robots could also generate these types of dynamics. So that's what we do. Okay. And so this is the title of the workshop today, and we're going to go through each of these points one by one. So let me just maybe recap again, like what we would like to do, especially specifically in neuroscience, at least one case study. And this was provided to me from Dr. Faber as an example of what she's done with brain regions over time. Okay, so this is a paper that was from PNAS 2017 called Brain Network Dynamics Are Hierarchically Organized in Time, which used a technique called hidden Markov models. So here's how it worked. What you can see is this type of time series, right? And each of these lines represents a region of the brain and its activation over time. Okay, so I don't know how many dimensions this is. Maybe it's 20 or 40 or something like that. So you have, these brain regions and they will, move, some of them will move together, right? They'll have like these correlations and move together and dynamically change together, and some of them won't. And when you have all of this data, what you would maybe like to do is figure out, are there any brain state patterns? Like, is there a brain state where we have both like I don't know, the premotor cortex and the I don't know, visual cortex like both activate at the same time? Like, is there some sort of brain state that's like that? And then if we can we, find these different states, so that's a B here, and swap between these different states. And we'd like to look at maybe how the brain swaps between like a default mode and some other mode, right? So that's these brain states. And some of the work that Dr. Faber has pointed me to is this cool idea of being able to find automatically these brain states and see how they might swap between each other over time. Okay, so that's kind of the inspiration of why I was like, wait, that's kind of like some of the work that we do. And maybe some of the techniques that we use could be useful for you too. Interestingly enough, this technique that was used in this PNAS 2017 paper, hidden Markov models, used to also be used in speech modeling, right? Dynamic over time. And HMMs used to be the way that we would be able to make like robotic sounding voices. Like back in the day, that was the technology that we would use. And today I don't know if you've heard the latest speech models, but they are like very, very realistic now. And they've gotten a lot better because of some of the techniques I'm going to teach you today. Because what happened was in 2017 at the Neural Information Processing Conference, some folks from DeepMind published this paper, the Neural Discrete Representation Learning paper. And you can see here the word that we see in our title today, VQ-VAE, and we'll learn what that means today, where they proposed this vector-quantized variational autoencoder, and it could do lots of interesting things. When you couple this VQVAE model with some other piece of neural network, you can generate high quality images, high quality videos, high quality speech, like that synthesized speech. And it even said you can do unsupervised learning of phonemes. Phonemes being, right, like the little units of speech, kind of like unsupervised learning of, I don't know, bird song or something like that. And so modern speech synthesis uses this technique. A word that you might have heard of or not is called tokenization. And so VQ-VAE, tokenization, that's the same term. I'm going to stick with VQ-VAE for the rest of the talk, but if you've heard of tokenization, that's the same concept. Okay. So similar to how we might want to find patterns in brain dynamics, in our work, we wanted to find patterns of body dynamics. So if you think about each key point on a skeleton moving through time, we could also come up with a plot that's kind of like the one that we saw earlier, where we have a point like the left hand. So that's just like one of these, it's like point number 20 here, in X, Y, and Z space. And for each of those, we could plot those dynamics over time, right? And so over time, a motion could also be represented in the exact same way, temporal dynamics. And so Payam, brilliant student, back in 2020 or 2021, he was like, wait, there's this cool thing I found at NeurIPS. It's like this autoencoder. It's really neat. Maybe we could use this to work with this gesture generation problem that he was working on. And so what he came up with was gesture to vec, and basically he's trying to not take like bird song, but take the language of body language or body gestures to try and figure out what's this motion vocabulary or gesture vocabulary that if you were to just watch a person for 3 hours gesture, what would be these little patterns that you would come up with, like little, and he did it, right? So he used this VQ-VAE to generate what we call a code book. And so you'll look at that today. A code book where each of these codes or like represents these clusters of motion. So you can kind of see here, this one is the cluster of this. I know my kid, I saw my kid, she's 6 years old. And so like, they're all like, oh, 6, 7. Yeah. So there's, that would be like one of the patterns and some other things like this, right? So we have found this like motion vocabulary. And so I think that's kind of what we would like to do with brains too, if we could with this technique. By the way, we haven't yet done it with neural data. So that's going to be up to you. But what I'd like to teach you is provide you all the code about how we do it with this, and then you can, figure out how it could be adapted to that. Okay, so yes, unsupervised pattern discovery is cool. And let's figure out now what we're doing today. So VQ-VAE is an unsupervised method for clustering in a dimensionality reduced vector space using artificial neural networks. So what we're going to do is we're going to go through all of these key points one by one. So the first part is that this is going to be a method which is automatic. It means we don't need to go through and provide annotations in our data. And we're going to be doing clustering, which is finding clusters of common patterns or sequences. We're going to be doing it in a dimensionality reduced way, which means that we will be working in a slightly more efficient space rather than on the raw data. And it'll be a vector space, which we'll go over later. And critically, we're going to be using neural networks to do this. Okay, so let's start with the first bit, which is the unsupervised clustering. Anybody here done clustering before on any data? Okay, all right. So let's just first start with this, which is unsupervised learning and clustering. So first, machine learning. I'm not expecting that have any background in machine learning, but what I can tell you is that there, at least classically, used to be kind of two types of machine learning: supervised learning and unsupervised learning. So supervised learning is this type of kind of task that we used to do actually before the big foundation model boom, which was we would take a huge data set of labeled cats and dogs and chairs and I don't know, birds, and we would train a model to be able to recognize them. So you would have all these labels of cheetahs, dogs, wolves, and then eventually once you train your model, that model would be able to say, here's a new picture, that's a dog. Or here's a new picture, that's a cat. So that was called supervised learning, and it needed a lot of annotations. But now in 2026, it's all about unsupervised learning. This is how we have ChatGPT. This is how we have these big foundation models. It's because in order to train on the world's data, they couldn't afford to just annotate every single thing. But what they got was data that they could find correlations in, right? And that's what the model is learning. And that's probably also why some of the fragility happens. But okay, so unsupervised learning, I'll give you an example. This is my husband, my daughter, when she was a little baby, and we lived in the West End, and she was a little unsupervised learning machine, okay? She would go around, and because there's a lot of birds around, she would kind of point. And I'm like, oh, she's getting the concept. She would point to the goose, she would point to the crow, she would point to the pigeon. And I'm like, oh, she's starting to get that there's some sort of pattern here. There's something going on. And we're not monsters. We also said oh yeah, that's a bird. We did the supervised learning part too. But before that, she had to actually come up with that, regularity on her own. And so unsupervised learning is that kind of thing that she's doing. It's trying to make inferences about these data with no labels. And you could do you could do an inference grouping and these data, trying to find anomalies oh, that's weird. That's not part of, the little model I had in my head, or finding these patterns in the data. And so when we put this into code, or if we try to model this, what this might look like is, and I'll talk about features later, being able to plot this sort of data like this, feature space, which don't worry, I'll talk about if it's not clear yet, and being able to find these clusters, okay? Now, what's the algorithm to do this kind of clustering? Can anybody name an algorithm that we might use to do clustering? Don't worry, because we're going to look at one right now. Okay, you might have heard about it. The one that's classic in machine learning is called k-means clustering. And I'm going to give you an example by talking about music, because I like music. Okay, here's an example. You have a music collection. It's your, I don't know, Spotify music collection. And let's say I want to discover groups of similar songs in my music data set. And this is your Spotify Wrapped at the end of the year, right? It's trying to cluster and figure out what are these types of similar songs that you do. And in mine, it probably has like, I don't know, Ariana Grande, like, musical theater, and then like K-pop Demon Hunters, like type of K-pop, and then like Paw Patrol because of my daughter. Like, it's just, there's groups, right? So for example, if you wanted to do this task, you would have to do something like take some features that are relevant to your problem. So for example, if I wanted to group some similar songs, yeah, you could probably do it by like lyrics and stuff. But let's just say I want to group them by like the tempo, like the speed, like generally how fast it is, and maybe the average pitch of the song. So like high pitch type of stuff, low pitch, like, so these are the different types of features maybe I could extract from each song to work actually with this data. And so this was a slide that I made when I was living in Japan, so you can ignore the actual songs here, but this is an example of how your data might be spread out, right? You might have some music that is fast and high pitched, and you might have some music which is slower and low pitched, right? So this is how your data might plot out. And k-means clustering means that you, instead of saying that all of this is a group, right? I want to say that actually there are two groups here, and one group has an average beats per minute of 120, and the other one has a beats per minute of 60, and there's some information also about pitch in there. Okay, so why is this called k-means? So here are our means, mean 1 and mean 2, and I have decided that I think that probably there's two groups or two clusters in my data, and now that k is a parameter that I can choose, and we can talk about that later about how to choose that number. But this is why it's called k-means, is because I decided k is the number of clusters, and I'm going to start with these two means in my data. And so the clustering algorithm, how it works, is that I initialize k-means for each of these classes that I think exist. So like these two types of music, for example. And I can just randomly choose the starting points. And how it works is that for every single song or every single point, I'm going to assign it to the closest mean. So if I randomly initialize my mean over here, then I can say that this song is going to be assigned to this group, it's this mean. But this song here, which is a bit, I don't remember what axis this was, but like higher pitched, slower, these ones would be assigned to this mean, okay? And it's an iterative algorithm. For every single one of these points, I'm going to assign it to the closest mean, every single one. And then when I'm done that, I'm going to update the mean to be the average of all of the points that have been assigned to it. So there's an update phase. Okay. And so this iterates. Once we do that, we have a new location for both of our means. And then we do it again. We assign each point to the closest mean, and then we update the means of new clusters. We keep doing that until it converges and the clusters don't change anymore, the means don't move anymore, and we have done our k-means clustering. Okay, this is going to be important because this is actually very similar to what's going to be happening in the VQ-VAE. Okay, now the thing to note about k-means, or what's special about it, is that it might do clustering, but it does something called like hard clustering, which means that every single sample or like every single song can only be associated to one of these clusters at a time. It means, so for example, like if I've come up with 3 different groups, each song is 100% assigned to that group. It means that a sample can't be like 20% jazzy and 80% classical. It's just hard assignment. Okay. And this is interesting because this is very related to the point of vector-quantized variational autoencoders, which is the type of thing we're looking at. Quantized means like discrete separation or discrete, I don't know, separation. I don't know. There's another word that I can think of. And that's also a key feature here. So unfortunately, like for better or for worse, we're saying that each sample has to be bucketed into one class or another. Okay, and that's the quantization aspect of what we're going to look at later. Okay. As a small aside, how to choose a number of clusters K. We're not going to go deep into this at all, but just so you know, there's some sort of like secondary algorithm that you can use to pick the number of clusters K, and it's a little bit of an art because that number we have to kind of look at the data sometimes to see what makes sense. But so you can see here, for example, if I said there's only 2 clusters in this data, that's a little bit underspecified. We can keep adding to K to say, okay, 3 clusters, not great. 4 clusters, 5 clusters looks starting to look pretty good, but 6 clusters looks actually quite good. And you can see that there are metrics you can use, like a silhouette score that you can calculate. I'm not going to go into it, but essentially it's a number that you see here is calculated, silhouette 0.662. It maximizes the silhouette score, and that actually gives us our best number K. And essentially what that silhouette score is measuring is like trying to maximize the distance between the clusters, but minimize the distance between the sample in each cluster. So yeah, not important, but just not for now at least, but just so you know. Okay, any questions so far? Yes.
Principal component analysis.
Principal component analysis will be coming up next. That's more about representation learning. So I'll talk about that in a moment.
In the whole space of unsupervised learning?
Yep.
How much is this? Like how is K-means like the big original one? Are there many?
I would say K-means is the big original one. There's also like a soft clustering method called Gaussian mixture models, which is another way to do clustering if you did want to have soft assignment. But those are the 2 big ones, I'd say. Any other questions? Okay. All right, so we did the unsupervised clustering, but we know some stuff about that. But now let's talk about this dimensionality reduced space and why that might be interesting. Okay, I'll start out with a little bit of personal story to kind of motivate this. I'm really interested in representation. It feels really elegant to me, like thinking about, again, how you can take all of the noise and try to boil it down to some more essential features. It started when this was baby Angelica, when I was in my master's in Kyoto University. So I started out in this lab, which did speech and music processing for robotics. And we made this robot to play music with us. And it was kind of cool. It was kind of this idea of dynamically adapting to each other over time. And like the robot would adapt to the beat, the drummer by using coupled oscillator models, blah, blah, blah. But the problem that I came away from was the following. And it's a question people are kind of grappling with today with music playing robots or music playing algorithms. If a robot or an AI generates music, is it real music? Like, if they just copied the surface, right? And so I was grappling with that question about 15 years ago, like, is there something deeper here, or is the robot just playing the notes on the page? And so I was really trying to understand what are these kind of lower level or essential features that humans use maybe to express emotion or to represent emotion. And that kind of got me thinking about representation. And so at that time, I was looking at these different factors of dynamics: speed, intensity, regularity, and extent. And I'll explain more about what that means. For example, in voice. So I'm going to play an example. I hope people online will be able to hear it. If not, don't worry, it's not that important. But here's a sample of an emotional voice that I used way back in my PhD. It's in German.
Heute Abend könnte ich es ihm sagen. Heute Abend könnte ich es ihm sagen. Heute Abend könnte ich es ihm sagen.
Okay, if I were to ask you, what emotion do you think she is expressing in German, what would you say? Yeah, people usually say either anger or happiness. And I think that one was actually happiness, but it's up to, it's, in the eye of the perceiver, right? But for me, what was interesting was like, okay, if I take some speech, right, something like that, and I extract these features of speed, intensity, regularity, and extent, and I'm just going to put that in a black box. And then I re-synthesize either speech or gesture or music with those type of dynamics. If people are perceiving anger or happiness on the left-hand side and they still perceive the same emotion on the right-hand side, that means just with 4 numbers, we could essentialize, we could represent that emotion or expression, right? That is a compact representation. And here I've crossed modalities, that doesn't really matter so much, right? But so this was what I proposed at the time. It's this representation of emotion dynamics called SIRE, and yeah, it could be used for a bunch of different things. At the time, the way I came up with this was super manual. I just poured through psychology literature. I poured through music literature, even some like neuroscience music stuff. And I was just trying to come up with these regularities by myself. Like, oh, look, this seems to be an important feature in all of these modalities. And oh, this also seems to be an important feature. Okay, this is also an important feature across these modalities for emotion. And like extent seems to also be an important feature. So 10 and 15, almost 20 years later, here we're like trying to figure out, is there a way to do this sort of thing and find a feature representation without having to manually make these little conversion models, without having to come up with these features by hand? Okay. And so, yes, answer will be yes. But what do I mean by representation? So let's just recap here. We have all these features. And as you kind of saw, that 4-dimensional representation of an emotion expression is also, you can call it a vector, which just means that it's a list of those numbers, right? It's 4 dimensionals, it has 4 numbers in it. Or in this case, it's 2-dimensional, so it has 2 numbers. And so when we say a dimensionality reduced vector space, it just means like going from a speech signal, right, to those 4 numbers, like a low dimensionality, only 4 numbers. And as I said, how do we decide those features? We might just come up with them, do something called feature engineering. Like if you're looking for features, diagnostic features for skin cancer, maybe it might be like mole size and darkness. And then, yes, then you can use something like PCA to try and find the best features or most prominent or important set of features for your analysis. So that's kind of the classic way that we would do that. But what if we could come up with these representations automatically? And that's where we are today. So we can use neural networks to do this. And the kind of headline here is that deep neural networks can be used as feature extractors. And when I learned this, it kind of blew my mind. I'm like, what? All of that time where I had to come up with these features by myself. And now these big neural networks can be used as feature extractors. And let me explain a little bit more. And it may or may not be useful yet for your work, but let me explain more and you can tell me if it's how useful it might be. So brief background on artificial neural networks. I don't need to explain this to you. We take inspiration from actual neurons, which have, the dendrites coming into the soma and then axon terminals, going to the output. The way we try to model this on a computer is using a perceptron, which represents one artificial neuron. But it works kind of in the same way, but not. So you can see here that we are trying to do a summation over the inputs, but each of the incoming inputs also has a weight coming into it. And each of these weights are probably tuned through experience for humans, and it's tuned through experience and training for neural networks. And then what happens is if the sum of all of these inputs, weighted sum of these inputs, reaches a certain activation threshold, this artificial neuron will fire and will give us output of 0 or 1. Well, it would give us an output of 1, right? It would give us that activation. And how do we do this mathematically? We we calculate all of that weighted sum, and then we put it into an activation function, which will allow us to, get like a 0, 1 out of it. Or in this case, I think it's maybe a -1 and a +1. Right, so this is the kind of function you would just plop the output from that sum into that x over there, and it would give us some number that we could then check to see if it's hits one of these binary thresholds. Okay. So that's a perceptron, and that was developed in the, I want to say 80s or even earlier, maybe 70s or 60s. Like it's really, really classic thing. And for a very long time, people were working on MLPs, so multi-layer perceptrons. That looks kind of like this. So you didn't just take one neuron, but like layers of them. And this says like 1980s neural network, right? So they were kind of sort of working at the time where you had like an input layer with many of these neurons, fully connected to a hidden layer of a bunch of these neurons, and then an output layer. Okay. I'm not going to go too deep into it right now, but what I want to say is that today's neural networks, which are deep, and this is the kind of deep learning boom that started in maybe 2012, has many, many, many layers. And one interesting finding is that these layers, when you inspect them, and if you're able to visualize these layers, you can actually see that they extract features. So a feature, for example, in terms of this input here, which is a picture of some famous American person. When you put it into these layers, it will do things like first identify these very like minute features like edges. And then the next layer will combine these into smaller, more distinct combinations of these edges. And then they will hierarchically kind of combine into these features that might even be used and understandable by humans. So that's what I mean by deep neural networks can be feature extractors. How does this work? I usually teach like introduction to machine learning, and this is like a whole class. So one slide, here we go. What we do is we perform something called backpropagation to train a neural network. And what this does is it's just, I'm not going to put any math on here. It's an efficient method to find optimal weights for our neural network. And we train our neural network by showing it a whole bunch of inputs and outputs. And it has to learn some sort of weight combination such that the next time it sees like a similar input, it'll output a similar label. This is for a classification task. So again, yes, you'll feed a training example forward through the network. It'll do all sorts of activations, and you'll get some like outputs on the output layer. But then your output may or may not equal what you want it to. So that means there might be an error. You will backpropagate that error back through the network, update the weights, and you'll just keep doing that over and over. That's kind of in a gist, like training a neural, what training a neural network means. Okay. And it's called gradient descent. Again, I'm not going to go into the details, but it's just a method to be able to find that optimal set of weights through a kind of sample efficient method to not just like brute force try all of the parameters, but try to find this gradient that leads you nicely into that optimal set of parameters in an efficient way. Okay. So yes, deep neural networks can be used as feature extractors, low level, mid level, high level. And usually this is done when you're training a classifier, like classify this person. This is George Washington. Okay. So you can try this if you're interested. You can input like a picture into deep neural network and see what happens in the middle layers. But here's one thing. Like today we talked about wanting to do an unsupervised method, which means there's no annotations. I don't want to have to use annotations, right? So what can we do to get rid of this whole annotation step? We can still train a neural network, but I don't want to use labels. this is, I'm going to do this briefly, and then I'm going to pass it to Payam, where we're going to have a chance to actually work with some of these neural networks on your laptops. But essentially, we're going to be using something called an autoencoder. And what that is, it's a deep neural network. It'll extract our features just like we want them, but all we have to do is make the input generate the same output, as you can see here. The goal of an autoencoder is to mirror the input to the output. And I want to train my network to get the same output as the input, right? Auto, self-encoding. And so it's a deep neural network where the outputs are the same as the input, or we want to train it to do that. And you'll still get, in the middle, this bottleneck layer, which will be a feature layer. And it'll be this good compact representation, kind of like my sire representation. It's a compact representation where, you know, the output, when you put it through, if you get the same output as the input, you're like, okay, it worked, right? Like my representation is meaningful enough to maintain the output as the input. And in practice, that means that after you train it to do this, you can use that, you can do the following. You can take some new input, like the number 7 here. You can throw it into the encoder, which is already trained. It's just a whole bunch of weights in that neural network. And then at the middle, you will just like cut off the decoding part. We'll just get rid of it. And you'll just like look at that embedding layer and the activations there, which will be like, you know, have some numbers, right? It'll be your vector. And you can use that vector and you can plot them. And you'll be able to plot them, and then you can do what you want with them. These are your features now. What do they represent? I don't know. I don't know. And some people will like poke at them sometimes to see, okay, if I increase this, what changes when they decode it? And then you can kind of figure out, oh, okay, this dimension of my encoding represents, I don't know, the eye width or something like that. And you can actually learn to understand what these embeddings represent. But to be honest, most computer scientists don't, because I'm just like, hey, I want to build stuff. Okay, let's just build more stuff. But you could do k-means on this, right? And that would give us the unsupervised clustering in a dimensionality reduced vector space using artificial neural networks, right? That would fulfill the thing that we wanted to do. We will show you like a slightly more complex version with the VQ-VAE in a moment. But first, I'm going to check on time, but hopefully we can at least get through some of these Google Colabs. So I'm going to pass it over to Payam, but in the meantime, if you'd like to open up colab.google.com, you can open a notebook using GitHub, and there's this stuff here. So let me just see. Yeah, okay, I'm gonna let Payam share his screen, and then I'll let him continue to do a demo. All right.
Okay, hi everyone, I'm Payam. I'm gonna present a little bit about how we use this techniques like k-means, autoencoder training, loading data, and so on in practice. So please open that link, and I'm gonna do the same and show you how we get started. So this link retrieve, this is not working. Or... Okay, this is the GitHub repository, and this notebook, 00 setup, set up everything for you on Google Colab. So now I'm gonna show you how we do this. The link, yeah. So everyone has the link. Okay, good. So yeah, our goal is to start from this 00 setup, and then we have 3 notebooks. I'm gonna go over them quickly, but how I do this, I start with Google, searching Google Colab. I open Google Colab, and then I copy this repository link, and here, once I open the Google Colab, I can create a new empty Colab or start from anywhere. I start from GitHub. Paste the link here, and then you will see list of notebooks you can open. So we start from the, sorry?
Takes a little while, but I think it should fix it up first.
Okay, now I have this opened on Google Colab. The thing is, you see here we have several files. So Google Colab usually works only on just one Jupyter notebook or Colab notebook, but we need also, for example, Salsa utils or VQ layers or utils.py plus our dataset. So this file does that for us. So I start from the first cell. Once I click on that, it asks to run, start a computer, an instance for us to run our code. And also it has code to mount your Google Drive. So this first block connect the Jupyter Notebook to your Google Drive, and it might pop up something like this, connect to Google Drive. And I need to give the access to the Jupyter Notebook. Yeah, you can take a look to the code. And we are recording the session. So, okay, awesome. So it is mounted. Now I can click on this file explorer, and I have Drive here. And I'm gonna show you files in my Drive. I also have it open here. So this is my just personal ROSIE Lab account, Google Drive, and this is my Drive, the root. And so I see files here again, similar to my Drive. Now, the second block gonna clone this repository and store it into our mounted drive, my Drive. So I click here. So it is very fast because it's less than a megabyte. So now if I refresh here, I can see that it should be, oh yeah, here, VQVAE INN workshop. So now I cloned those Salsa utils and so on. Next is about going to that directory in this Jupyter Notebook. Just click on this cell, and then we can start downloading our data set. So for example, this is the American Sign Language data set. I'll explain it later. And this is our Salsa data set. And this is some pre-trained model. So because training takes some time, I also provide the pre-training. So I'm gonna hit this Salsa, for example, so to show you how it works. So it is downloading, and the data set size is something about a gigabyte or so. Oh, it is less than 400 megabytes. And then immediately after, it starts unzipping that. So you see inflating our data set. Again, I'm going to this, that the data has downloaded. So now we also have the data folder and the Salsa data. This is the zip file we downloaded, and this is the data set itself. We have validation set and training set. So the reason I downloaded this data first, because it has less file to unzip. This one, the American Sign Language, because we have lots of American Sign Language emails, it takes some time. Also, after you unzip in Colab, it takes some time to appear on your Google Drive. So if you immediately go to the next step, notebook number 1, you might see that you don't have access to data. It takes few minutes. But so this is, you see, downloaded and inflating. I can refresh. Oh, it is already here. ASL data. And it is unzipping. So this is about the setup. So now let's assume that we have set it up. Now I want to move forward. I want to move forward and start training another model. So I do the Google Colab, search again, and then open a new Colab. Then I have the link to my GitHub repository, GitHub, click, then it lists the notebooks. We did the step 1. Now we move to step 0. We move to step 1. And we have, let's assume we have the data. Again, in this Jupyter notebook, we have to mount our drive again to give access to utils, .py files, other dependencies, and the data set. So run anyway. And then once it is mounted, we move to that directory, cd. So it wants to get the access again. Continue. So yet it is not connected to our drive. It is loading. So the Google Colab is a little bit slow. If you can run even on your laptop, it will be faster. Then so now drive is mounted. My drive, the VQ workshop folder is here. We see the data and so on. So I move to that folder. Now I can start doing regular things I could do on local machine. So the first 2 blocks for those who wants to use Google Colab. So we import some dependencies. I don't want to talk about details, like technical details, but in general, when we want to train a neural network, we have data set, we have model, and we want to train the model on those data. So first, the data. We need to load the data and batchify the data. The reason of batchifying the data, it means that if let's say we have 1,000 samples and we want to train our network on those 1,000 samples. If we train on 1 sample, it's like you feed 1 sample, you see the output, you calculate the error, and you want to adjust your weights. So the training curve would be jumpy because every sample draws our loss function to different directions. And if we feed the entire, we calculate the error on the entire 1,000 samples from our data set, so it would be meaningless. It would be average of everything, so almost nothing. So that's why we batchify. We, for example, take 32 samples. 32 samples goes to the network. We see the output, error, weight adjustment, or backpropagation again and again. So this is the data, and then we need to define our network architecture and the training process. We have 2 for loops in general when we want to train the networks. First for loop, iterating over the epochs. Let's say we want to train our network for 100 epochs. So 100 times we want to calculate error for all of the data set. That would be outer for loop, inner for loop over our batch or over our data. So having that in your mind, so we want to load the MNIST dataset. MNIST dataset is that digit numbers Dr. Lim was showing to you. So the MNIST dataset is very already prepared. So just with this few lines of code, you can download it and prepare that for the training. Here, we define our latent dimensions, which is 32, for example. We can even use 2 dimensions to represent 28 by 28 images of handwritten digits. And we define our model. The model is linear autoencoder. I won't go to the details of this model, but it is in our UTs files. You can later inspect that. And the trainer, we define that trainer, autoencoder trainer. And we want to train, for example, for 10 epochs and start training. So it
By linear, you mean just linear vision.
By linear, yes, we have linear. I can show you the network architecture. I stopped the training here, but let me quickly, very good question. Print the network, the model, to show you what's inside. So we see that we have a linear model, a linear layer. It is 784 equals to 28 times 28. We have handwritten images of 28 pixels by 28 pixels. So we flatten all the pixels in one dimension. That's why we say this instead of 28 by 28. Then an activation function, tanh, and then another linear layer to make the network more complicated.
Is that you're vectorized?
Sorry?
So you're vectorizing your image and then using hyperbole.
Yes. Yeah, tanh hyperbole. And very good point. You were asking about PCA. The difference between this and PCA is just that activation function, tanh. Otherwise, it would be exactly same as PCA. So PCA is linear dimensionality reduction approach. Here we have non-linear. How we add non-linearity to the network? Using activation functions. So yeah, I skipped that. And then after training, let's assume that we have trained the network. So from now, I move to my local machine because it is a little bit faster to show you instead of on the Google Colab. So I should start from loading data. Is it good now? One more time. Okay. So yeah, import things and then load data and then defining the model. Look how it is fast on my machine compared to the Colab. And I'm gonna stop it after epoch number 2, but you can train more and you get better results. Like, I guess for this example, you need 20 epochs. So now we have model trained until epoch 2. Let's inspect that. So we have latent space clustering colored by digit. So here we are loading our data, feeding that to our network, to our model, just the encoder. This is where Dr. Lim was saying about dropping the decoder, only keeping the encoder as our feature extractor. So this is model only encoder data, and we get the feature. This Z represents our latent space data. So we append that, and then we use actual labels from the digit labels. Our training was unsupervised, but here we show the results using actual ground truth labels. And we use scatter latent. It's a function that reduces dimensionality to 2. It's just for visualization, no training, nothing related to deep learning. So here, yeah, when we say latent, it means that vector in the middle of the encoder and decoder we were showing. So you see that even with 2 epochs, when we color features based on actual label, the digit number, we see that they are well separated. It means that we are doing good. And but here we use the supervised labels. Later we move on to k-means and so on. Also, another thing I want to show you is using both encoder and decoder to see final output.
You have 32 dimensions, right? That's your encoding.
Yes.
How do you choose, how do you reduce those 32 dimensions? Because you're just showing 2 dimensions.
Oh, yeah, you're asking about this plot. Yeah. This is called t-SNE visualization. Again, it's completely separated from our training process. It's just for visualization when we have higher dimensions, like 32 dimensions, and we want to visualize in 2D dimension. It is an algorithm that brings relative distance in higher dimension to lower dimension. So when you see here, this x-axis and y-axis means nothing here. Just the distance between two samples here is similar to their distance in higher dimensions, in 32 dimensions. So and every time you run this, it is a randomized process. You get slightly different visualization. And so here, and you saw that for this visualization, I only use the model encoder. I skipped the decoder. Now here, I want to show you results from the reconstruction, which means we load the data, we feed it into the model. Model means both encoder and decoder, and we see the reconstruction. So I click to show you. See, even with 2 epochs, we get good outputs. So from now on, we have 2 more notebooks. Almost every step is similar. We load the data, we make the model, we train the model, we visualize latent space and outputs and reconstruction. So I move to the second slide. How much time?
If you show us 2 slides before we go to that, just to
Yeah.
show the theory, and then we can go to those. Yeah. Okay. Okay, so that's where we were. Thank you, Payam, for showing us the autoencoder and how that works in practice. So we okay with what that was doing? Yeah, we were trying to just encode our data into a smaller representation, and then we used a neural network to do that. That's it. Okay. And we were working on just pictures. I know this whole workshop is about continuous data, so we will get there. But first, I'm going to talk about the VQ-VAE because we didn't do that yet. Basically, what a VQ-VAE is doing is instead of like doing this and then getting this representation and performing k-means at the end, the VQ-VAE incorporates that k-means idea into the training process. So that's what we're going to do now. I'm going to talk just briefly about what the VQ autoencoders do. So again, this is this paper from 2017 from NeuroAIs. And at that time, what they did was they were still working with pictures, for example, and they were encoding them and trying to decode them, kind of like what we did. But at the same time, what they did was they slotted in this k-means piece in the middle. And what you see here in the middle is, here's our first mean, like mu1. Here's another one, mu2, mu3, all the way down to mu53. These are all our means that it's trying to calculate. And it's doing this gradient update while doing all of that. And I'll show you in a moment what that looks like here in this nice animation that Payam has made for his work. So what that is first during training, we take each sample and we encode it into this little vector here that you see, that little encoding, that little, right? It's like shimmering there. And then when you take, afterwards, you take that encoding and you do, you see all of the means that are already existing and you calculate the distance, right, between that new sample and all of the existing means, right? And you assign it to a cluster, just like we did with k-means, right? And then we're going to update the means of the new clusters. It's the same idea, but in latent space, in this hidden lower dimensional space. So it's not exactly that, but it's very, very similar. It's that idea that we are now doing k-means clustering in this, new hidden, this new space that has been defined by our neural network. Does that make sense? Ish. I haven't gone into any of the details about how that works, and I'm not gonna talk about the math that like is able to do this. But the general idea is that this gesture, like this code book, represents all these different cluster means that we used to have in k-means clustering. And that is, all of these means are being updated and assigned throughout the training process. So it's just doing k-means in the middle of training instead of at the end. Okay, so I will pass it back to Payam, and then we can look at the code to see how that works.
Yeah, to simplify, I mean, the intuition behind VQVAE is similar about the image reconstruction that Karim was explaining. It's like, for example, for each pixel, we have RGB, each has 8 bits, 2 to the power of 8, 256 different numbers for R, for G, and for B. Assume that what would be the combination? 2 to the power of 24. But in practice, human understands red, light red, dark red. This is the VQVAE. We do not touch about exact RGB values. We say red. It might be slightly light red or dark red, still red. So that's the intuition behind VQVAE. So I move to the second Jupyter notebook. It's about hand key point autoencoder. In previous notebook, we trained autoencoder on 28 by 28 handwritten digits image. Now we want to train on another type of data, which is key point 3D of one hand showing American Sign Language words, letters, like, for example, A, B, Z, and so on. So again, the data is slightly different. Previously, we were using image. Now we have 3D key points. And that reduces the dimensionality significantly. There we had 784 dimensions. Now we have 21 joints, each represented with 3D dimensions. So it would be 21 times 3, lower dimension. We learn better representation. I show you. So again, we have this after doing the Jupyter setup. We can, if we're on Google Colab, we should run this 2 blocks. Next, I move to import. I import the libraries and dependencies. Here you can pick some letters because there are 26 letters and it takes so much time to train. And also some letters are similar, are not easy to. Should I? Oh, it's not.
There it is.
So I picked these letters that they are honestly very discriminative letters in terms of hand key points. So, okay, I hide it. Okay, I ran it. Now we have the data train loader and so on. Now we want first to visualize the data. Let's see what's inside the data. So we have, let me change the number to something else. That was not a good example. So the reason is we extracted this key points using a library and it is not very accurate. So it's not very good example. I wish I could find oh, here. This is a good example. See, it's almost there. So this 3D key points are our data extracted using a third-party library to extract these 3D key points. Now we want to train autoencoder on our 63 dimensions. So again, we have to define our linear autoencoder dimensions and so on, and the trainer, very similar to previous one, and it has 10 epochs. Look how fast it is compared to when we were training on image, because we have lower dimensions. So how we get this lower dimensions, we use a third-party library that we can call that as another layer of feature extraction, 2D image to 3D hand key points. But here we started from 3D hand key points and we trained the model, just trained. Now let's see a reconstruction example. Reconstruction means we use this one to the encoder, latent representation goes to the decoder, and we get this output. So sometimes it is not exactly what we had before. See, this is the error of our network, for example. So I move forward. Now we want to see the latent space visualization, very similar using Tisney representation and colored by ground truth labels, similar to the previous one. So here we see they are very well separated, and this is thanks to our 3D key points, which was extracted using third party. So this is again an importance of the data representation. So see, they are completely separated. But our task was unsupervised. So we wanted to apply k-means. So here I apply k-means, and instead of using labels from the ground truth, we use labels from the k-means. So let me hit the run here. So k-means applied. And the thing is, we also know the number of clusters. This is cheating, but we're using the actual number of clusters. Dr. Lim explained we can use silhouette and other metrics to estimate the number of clusters. So we said we have 12 clusters and they are completely correctly clustered. Now we want to train VQ-VAE, we explained. And here, all of these notebooks are very simplified. You can simply train autoencoder, load your data, or train VQ-VAE, but under layer, there are lots of, like for example, here we have VQ layer implemented this VQ-VAE for us. So we simply use that. The training is a little bit slower because we added a new component to our network. So it is training. Let me see how 10 impacts. So almost done. Now we want to visualize VQVAE latent space, but this time for labels, we use VQ code, which is the index of quantized. You can go deeper and see how we do this. I skip that for now, but just show you the results. So now we use our encoder, extract features, latent space, and calculate the distance to the nearest mean in the codebook in our VQVAE and assign that label. Still, we do not know, for example, this red one is representing what letter in sign language, but we unsupervised, using unsupervised learning, we understand, for example, this cluster is very close to this one, so they should belong to each other because the distance of this two compared to distance to others is okay. So this was VQ-VAE on hand key points, still static data, just single frame hands.
Thank you so much. We're almost there, and it's good because I think we have only a little bit of time left. So I'm going to stop your screen share here and grab back the slides. So now we just did VQ-VAEs on static data. That was just on poses. Okay, so they were like not sequential. So now we're going to go on to sequential data. And the only difference really here is that you have to do the representation learning twice. The first time you're going to be doing that representation learning autoencoding on each frame of your video or each frame of your brain data, whatever. And then you're going to do it again but on blocks of sequences. So like you'll have all these frames now that are represented by, this vector, and you'll take like a 1 second chunk of those and then encode that again. Okay, so I'm doing a lot of hand waving, but that's essentially it. In order to represent sequences, you just represent first the frames, and then you represent the sequence using that same technique that we did. And yeah, so now each of the clusters, they represent motions instead of just static poses. So with the time that we have left, I think Payam's going to show you the code to do that. And what we've done is in our lab, we do fun things like record salsa dancers in our mocap lab and then try to represent their motions using, this is all Payam's work, represent their motions in a lower dimensional space, reconstruct them. So this is his, I think maybe the representation, but reconstructed and revisualized, and then clustered them to find these motions that they keep doing, like these spins, like these are all coming from different dancers, clustering their motions. So I will let Payam show you notebook 3.
So I'll quickly also show you how we did this results of clustering salsa dance. They are a sequence of whole body. We do not have fingers, but we have 21, 22 joints, like neck, shoulders, elbows, knees, and so on. So this is the Jupyter Notebook number 3, Salsa Dance Motion Autoencoder. Again, you need to do this too on Colab. So I start from importing things. So I imported that, then the load data, very similar, but here is the thing. I told you we have, in any network, we have loading data, we have defining the network architecture, linear, GRU, CNN, whatever, and the training process. Each of them could be customized. The first one, the MNIST one, was the most simple one in our notebooks. But as we go, we customize each component. Here, we customize the network architecture, the data, how we load the data, and so on. You can go through the details. I skipped that. So we loaded the data. Now let's visualize one of the data. This is just grabbed from the ground truth. You see that this is a sequence of 19 or 20 frames of dancing salsa, randomly picked. We can do that. And since we are using next, we get different example. And so these are our data, 3D joints in 3D space. Now we define the model and do the training. So the thing is, because this is more complicated data, sequential data, and we have more complicated network. For sequential data, we use GRU instead of linear layer. So the difference of GRU and linear layer is like linear layer sees a ball in the middle of the sky, but GRU sees the track of that, so it can predict the next step. So that's the difference, and it takes so much to train. So I have a workaround for you too as well. In the notebook 0, you can download pre-trained. How I saved them, I did the train like 50 epochs, and then I saved using this block of code. I commented that, and now I only have the loading part. So I load the trained model. Now let's do the reconstruction. So the reconstruction shows original. This was the original sequence, and this is the reconstructed one. So if you see them side by side, you will notice that we have lost some of the details. That's the network error during the training. So we lose some of the detail, but still it is representing the same thing, and we can say the latent space is meaningful. So another example. And then again, we want to visualize the latent space. I don't hit this play button because it takes some time, but this is our latent space. And this time we really don't have the labels. Previously we wanted to compare versus, but now we do not have, so we can't color this latent space or encoder output or feature vectors. So now k-means play an important role. So here I picked 512 cluster. This is just an assumption I made, and then I cluster them based on color. But as we explained, VQVAE is like involving that k-means clustering into the training process. So when we use k-means, it means that we already trained our network. So the network was trained for the reconstruction purpose, not specifically for very well latent space for clustering. But when we incorporate the VQVAE, it means that during the training, we push our encoder, we push our decoder, every component of our network to generate a better latent space for clustering purpose. So, and we add some VQVAE loss into our loss term. It means that we recompensate our network based on our purpose, which is clustering here. So again, I do not train the VQVAE here, but you can go ahead and do that. I load the pre-trained checkpoint. Did it work? Oh yeah. I hit this. Then I stop, and now I can load the pre-trained model. So this is the pre-trained model loaded, and now I can see the reconstruction of it. So this is the original, and this is the reconstructed. Very bad, because we previously when we were training autoencoder had just one loss term, the reconstruction, mean square error. So we wanted to focus on just output quality, output performance, just one loss term. Now we added lots of like k-means, sophisticated k-means, VQVAE loss terms. So we have a trade-off between what we get at the output and what we get in the middle of the network. So we get better latent representation, but worse output. But honestly, this is very bad because I trained for a few epochs, for like 50 epochs. If you train it for like hours, you get very better outputs. And then visualizing the latent space. So you see that it is well separated. So output quality lower, but latent space for clustering is way better. So this is how, let me quickly show you again. So this was when we were doing just regular autoencoder. No VQVAE loss term, no clustering intention into the training. And now you see when we train our network for clustering, we get this kind of results. Now let's grab some of samples inside one of these clusters and see what we get. So I picked cluster, for example, number 3, and I asked for 3 samples inside that cluster. Let's see. Oh, yeah, we have. So it seems about right hand raised, something like that, but not very good cluster. Let's move to, for example, cluster number 4 to see what's inside. Yeah, they are more similar. So yeah, that's it.
This took a long time to build, so I afterwards big like kudos to Payam for putting this together. It's like the last piece of his thesis. So, all right, we're coming up to the end. I'm gonna kind of skip this, but basically we're wrapping up. We did this, right? We figured this all out. We made it. We got this unsupervised clustering method. We looked at a couple different ways to do it. We figured out how we could cluster in this dimensionality reduced vector space. And we figured out how we could do this using neural networks. So what's next? For those of you who would like to use this for credit, I think I'm going to probably send a follow-up email to kind of confirm what we'd like you to do for the next steps. It'll be something like the following. Sorry, just here. Like, think about how you could apply these techniques to the type of data that you're working with. In the code, can you find where to adjust that? Just have a deeper look at the code. You can think about things like some of the other parameters, like learning rate. And so this is the data that is on the brain, and it talks about like clustering and finding these states, which would be kind of like these codebook bits similar to that, and being able to like go and see how these transition during states. So I'm going to send probably this paper or the paper that this was based off of, and I don't know if it's this paper or the other ones, probably your paper, right? Or the other.
This data is as yet to be published.
Oh, okay.
What spoilers for the event?
Oh, okay. Well, from the neural data, what we had here was things like fractional occupancy. So you could see like in the brain data, people spending time in state number 6 was like the highest amount, right? So I want you to try to draw parallels between the neural data and what we saw today. And that's one of the questions was like, I will send these slides later, but how would those blue bar graphs in the previous slide here relate to like the Salsa dance data set that we saw and the types of information that we could glean from that? So yeah, I think that's basically it. And then we'll have time for questions. Thank you so much. And big thanks to Payam for all of those words. All right, so I think we have no time for questions. How do you want to do this, Dylan?
I have to run also.
Yeah, I'm happy to stick around if anyone wants to ask specific questions, but we will follow up over email with the slides and kind of the workshop details stuff for the credits.